Ever wondered what a life-saving antibiotic, the gas that knocks you out for surgery, and a hormone your body absolutely needs could possibly have in common? I mean, they seem like they're from completely different worlds, right? But it turns out their incredible power comes from the exact same tiny molecular trick. It's a fundamental piece of organic chemistry that, you'll see, shapes our world in some really surprising ways.
Okay, first up, let's talk about chloramphenicol. This is an amazing chlorine-containing antibiotic that microorganisms actually make themselves, and it's incredibly good at fighting things like typhoid fever. A total lifesaver.
Then you've got something like halothane. This one's synthetic, and it's an anesthetic. It allows for these complex, safe surgeries that, let's be honest, would be completely impossible otherwise.
And finally, thyroxine. This is a hormone your own body produces. See that iodine atom in there? Its whole job is to keep your metabolism in check. And if you don't have it, well, things start to go very, very wrong.
So you've got a natural antibiotic, a man-made anesthetic, and a vital human hormone. What on earth is the secret link here? The answer, it turns out, is surprisingly simple, but it's also incredibly powerful.
They all belong to this huge family of molecules called haloorganics. And that common thread, that secret I mentioned, it's just a simple chemical tweak. Swapping out a hydrogen atom for one of the halogens. You know, fluorine, chlorine, bromine, or iodine.
Let's get a bit more formal for a second and introduce them properly. So, you start with a basic hydrocarbon, just a simple molecule with a carbon skeleton and a bunch of hydrogen atoms. When you pluck off one of those hydrogens and stick a halogen in its place, you get either a haloalkane or a haloarene. It's all in the name, right? Halo for the halogen, and alkane or arene for the carbon backbone it's attached to.
So what's the difference between those two? Well, it's all about where that halogen decides to attach. In haloalkanes, the halogen is bonded to a carbon that's part of a straight or branched chain. But in haloarenes, it's stuck directly onto a carbon that's part of a super stable aromatic ring, like a benzene ring.
All right, so we've got this massive family of molecules. How do chemists even begin to keep them all organized? Well, they classify them based on their structure, because as we're about to see, a molecule's shape and its immediate neighborhood completely dictate how it's going to behave.
So, chemists use two pretty simple methods here. The first one is a breeze. You just count the halogens. Mono if there's one, di if there are two, you get the idea. But the second method is way more important for figuring out how it's going to react. We look at the carbon atom that's directly holding on to the halogen, and we ask a simple question. How many other carbons is it attached to? If it's just one, we call it primary. If it's two, it's secondary. And if it's connected to three, it's tertiary. And believe me, this tiny little difference has a huge impact on how the molecule acts in a reaction. Now this slide right here, this shows us the molecule's reactive hotspot. Halogens are what chemists call electronegative. Just think of them as electron bullies. They tug the shared electrons in the bond way closer to themselves. This gives the halogen a little negative charge, and this is the crucial part, it leaves the carbon with a little positive charge. That slightly positive carbon becomes this glowing target, just waiting for other molecules to come in and react.
And that polarity, it affects their physical properties too. As you move down the halogen family, from chlorine to bromine to iodine, the atoms just get bigger and heavier. This beefs up the forces between the molecules, which means you need to crank up the heat to pull them apart and get them to boil. And you can see that trend perfectly right here. The boiling point for the chloro compound is the lowest, the bromo's in the middle, and the iodo is highest. It's all because those bigger atoms create stronger sticky forces between the molecules.
Okay, so we're getting a handle on their structure and properties. But these molecules don't always just pop up in nature. So how do chemists actually make them in the lab? Let's take a look at one of the most common recipes they use.
For chemists, alcohols are an awesome and super common starting material. The basic playbook is you take an alcohol, you react it with a concentrated halogen acid, and you basically just swap the alcohol's OH group for a halogen atom. It's a really fundamental go-to move in organic synthesis. Okay, now here's where things get really, really cool. I want you to look at your hands. Go on, look at them. They're perfect mirror images of each other, right? But you can't lay one perfectly on top of the other. They just don't line up. They're non-superimposable. Well, it turns out a ton of molecules in chemistry have this exact same property. It's called chirality, or just handedness.
And this brings us to a really critical question. If you have a left-handed molecule and it goes through a chemical reaction,
What happens to its handedness? Does it stay left-handed? Does it flip and become right-handed? Or do you end up with a mix of both? The answer, as you'll see, is all about the journey the reaction takes.
And to understand that journey, we have to look at the two main ways these molecules react. I want you to think of it as a story, a tale of two reactions with totally different personalities and styles, the SN1 and the SN2.
So here's the quick overview. The SN2 reaction is like a perfectly synchronized dance. Everything happens in one swift, coordinated step. A new molecule attacks from the back just as the old one is leaving. The SN1 reaction? That's more like a two-act play. First, one group has to leave the stage, which creates a flat intermediate, and only then does the new group make its entrance.
Let's zoom right in on that SN2 reaction. Here, an incoming molecule, we call it a nucleophile because it's looking for a positive nucleus to bond with, it approaches that slightly positive carbon atom. But wait, it can't attack from the front. That big ol' halogen atom is in the way, blocking it. So it does something really clever. It pulls off a backside attack, sneaking in from the opposite side.
Now, for a tiny, fleeting moment, that carbon atom is in a very crowded, very high-energy state. It's kind of bonded to both the incoming group and the outgoing halogen. That's 5 attachments at once. This thing is called a transition state, and it's incredibly unstable. You could never bottle it or isolate it.
And here's the magic moment, the payoff. As the halogen finally lets go and leaves, the rest of the molecule just pops into its new shape. The source material uses this perfect analogy. It's exactly like an umbrella flipping inside out in a strong gust of wind. The molecule's handedness, its whole configuration gets completely inverted. A left hand becomes a right hand.
The SN1 reaction, though, is playing a totally different game. In the first step, the halogen just leaves all on its own. It just goes. This creates a flat, positively charged intermediate called a carbocation. And because this thing is flat, like a little pancake, the new molecule that's coming in can now attack from either the top or the bottom. It has an equal chance. And what does that mean? It means you get a mix of products, some that have the original handedness and some that have the new inverted one.
So here's the crucial takeaway. Molecules don't just blindly follow one path. Very often, there are several different reactions all possible at the same time, and they're all competing with each other. It's basically a race.
And the source material puts it perfectly. A chemical reaction is the result of competition. It is a race that is won by the fastest runner. These substitution reactions we've been talking about often have to compete with another type, called elimination. And the winner, the reaction that actually happens, all depends on the molecule's structure, the strength of the attacker, and the conditions you're running the reaction in.
So think about it. We've seen how one tiny change, just swapping one atom for another, can create medicines that save lives. And we've seen how the very handedness of a molecule can decide its fate in a chemical reaction. It really makes you wonder, if something this small can literally be the difference between a cure and a poison, what other invisible molecular rules are out there, quietly shaping the world all around us?